Brings me to the next speaker. Yes, he's here. It's Arnaud Sartelet from University of Liège.
Yeah.
We're going to talk about a stop gain in the laminin alpha 3 gene affecting the Belgian Blue cattle.
Okay. Thank you. Good afternoon. We are waiting for the presentation, I think.
I think it takes slightly longer because we had to change the systems, but it will come.
I think so.
I think I should have given a longer introduction, but I...
No. Okay, good afternoon, ladies and gentlemen. First of all, I would like to thank the GIGA Research Center and the European community for the funding, and also all the people who work on this story on Belgian Blue cattle. So now, just few words for introduction. So everybody knows that Belgian Blue cattle breed is well known for its muscular development and also for its ease to calves by C-section. And then to have this muscular development, intensive selection, and mostly of the time extensive use of artificial inseminations, leading like in other species, other breeds, specialized breed like Holstein or Belgian Blue or other breed, you have the outburst of inherited defect in these breeds. For example, blood in the US cost close to in the 90s cost close to $5 million for the dairy industry, and so it's very important to try to manage inherited defect in cattle in our practice. And so during the last decades, we benefit of new evolution tools and knowledge in bovine genome. First of all, with the discovery of the bovine genome in 2009, and also now the available SNP chip, big SNP chip, I explained one colleague just before, and also the new technology, the high throughput sequencing and transcriptomic, who facilitate and accelerate all the process of determine genetic defect. So in Belgium, since 2007, with the collaboration of the vet and the vet and the breeders, we put in place a neurosurveillance platform to manage inherited defect. It's very easy in Belgian Blue because the vet is always present at calving for the C-section. And since 2007, we at least collect more than 1,000 cases, and we eradicate 7 inherited defects, like we have some example on this slide. But in 2015, we have 2 calves, 2 half-sib referred to the vet clinics in Liège, and this calf present big skin erosion on the mouth, but on the nose. But when you go in the mouth, you have skin erosion on the palate and also on the tongue. And one of the most important lesions is on the foot, with the absence of horn on the claw and the skin erosion on the feet. And when you go to the histopathological analysis, you have a dermal-epidermal disjunction, like here, the white line between the 2 layers, without inflammation signs. So with these 2 half-sib and 2 cases that we collect also in 2 different farms in Belgium, we decide to use a genome-wide association study. We're using SNP chip, so it's like present our colleague before. It's a little SNP where you can genotype all the SNP in the bovine. And we find, using program, we find a small region on the chromosome 24, a region identical by descent. So identical by descent just would like to say that the calf receives the same part of the genome, came from his father and his mother, but this piece of genome traced back to one common ancestor, is probably the founder of this disease. And we suspect that this small piece of DNA present the causative mutation. So to go more deeper, we use now a transcriptomic analysis. So we sequence the RNA to see if the genes are expressed in several tissues, and we focused on this region. We focus on the skin, and a lot of gene present in the small region is highly expressed on the skin. And one of well-known genes involved in epidermolysis bullosa is LAMA3, as it highly expressed in the skin. So now the next step is using classical sequencing, but with the new tools we have a lot of data with the 100 genome project or European project to sequence to sequence a lot of sires and cows. So we use it to find if there is one of the animal in the pedigree maybe already sequenced. And one of the grandfathers, named Félicien, an artificial insemination sire, was sequenced before to elucidate the story of the color-sided pattern. So we're looking for the sequence of these sires, and we find in the LAMA3 gene, as expected, we find the mutation in guanine to adenine transitions, leading to an apparition of a premature stop codon, leading to a 20% truncated protein, leading to the ineffectiveness of this protein. So now LAMA3 is an alpha-TRA subunit of laminin, okay? And the laminin is a part of, you have alpha chains, beta chains, and gamma chains. And the LAMA3 is code for an alpha chains involved in the laminin 332. So when you look on it's well known and is involved in the cytoskeleton of the skin basement membrane, and a lot of mutation in this gene is well known in mouse or in humans to provoke epidermolysis bullosa syndrome. So here you have a cartoon of the skin with the cell and the lamina densa, and here you have the laminin 332 and all the other protein involved in epidermolysis bullosa. You have just junctional epidermolysis bullosa. So we can validate this mutation as the causative mutation. So we develop a diagnostic test and we estimate the carrier frequency out of 3,000 sires. 300 sires, we estimate the carrier frequency close to 1%. So in Belgian Blue, it's not very important for us, but we can manage the frequency of this disease. If the carrier frequency increase, we can propose the test for the breeder. So the take-home message, more than the beautiful story, and if you need more information, you can find it in the paper already published. But the most important thing that we need to keep in mind is that 10 years ago, to eradicate a defect, we need close to 5 years, and we need 100 cases during these times. But now, with only 4 cases and 5 weeks, you can find the mutation and find the solution to eradicate this case. So in conclusion, the accumulation of the genomic data, genotype sequencing available with the all worldwide project in Belgian Blue and in Holstein is very rewarding. And to finish my presentation, it's a cartoon of a well-known Belgian drawer, Pierre Kroll, and he said just the mutation in Belgian Blue, the story continues. Thank you.
Thank you very much. Any questions? Okay, wait for the microphone, please. Thank you.
It was a lovely presentation, and you've obviously been very successful in finding these mutations in Belgian Blue. And I was just wondering what your success rate is. I mean, do you know that these are recessives, 100% recessives before you go after them, or do you have cases where there's maybe incomplete penetrance or something else? And what's your success rate of finding these mutations?
So I just present in the paper. You have just a successful story, and we just focus on recessive defect. On my part, I just focus on it. But we have some. We focus also, like our colleague presented before, like atresia or growth retardation, and so it's just wrong with cleft palate. We haven't a successful story, but we try to continue. But Belgian Blue is very, very good breed for this because it's very local breed, and with large artificial insemination use. So it's very easy for us. But now it's the breeders change and try to avoid inbreedings, and also the use of a lot of genetic tests. Now they need to use the pedigree of Belgian Blue and try to increase the genetic variability in Belgian Blue.
I find it really impressive that you can find a genetic defect in such a short time. I'm really stumbled by that. But so you will find lots of. Do the breeders experience that they can't breed anymore because of all the defects they have to take account? Is it becoming complicated in the Belgian Blues or?
Yeah, it's complicated, but as I said before, now everybody in the Belgian Blue world, breeders and artificial insemination center, now they try to keep the son of carrier sire. It's the goal of to keep the better son of these sires, to keep it with free, testing the mother and try to keep the free son. And also they try to increase genetic variability, going in fresh blood without not a lot of use. But it's a change in Belgian Blue, because a lot of times they do a lot of inbreedings to improve and to increase muscle mass, and now they said, okay, we lose a lot of muscle mass, but in fact we have some healthy calves.
Okay.
Yeah, you mentioned the sire, the bull there, and that I assume is one of the most spreader, or the founder of the novel mutation. When was the bull born? Because we know that between the novel mutation and let's say the discovery or the perception of the disease as a problem usually elapses many years.
Yeah. So the sire is not the founder sire. It's a recent sire that we used in the forest coloside pattern, and a lot of people use it because it was a beautiful color for some of breeders. So it's a sire of the 5 or 6 years ago. But when you get the pedigree, you have two cases. It's half sib, and it's a grandfather of the grandfather of the father of the calves. But the two other one, we don't have any pedigree, so it's not possible for us to trace back to the common founder. So we just use it because we find it in the pedigree, and we said, we sequence for the colocided pattern, and then we say we can use it for research and to accelerate the pattern. But it's not the founder, we suppose. And it's not very broadly used because its phenotype is not very good for Belgian Blue. Its color is good, but the phenotype is not very good.
Okay, thank you very much.
You're welcome.